A last very interesting feature of the symbolic toolbox is the code generation. We can take a symbolic function in MATLAB and call the C code command on it, and this will actually give us the C code representation of the symbolic variable, meaning that we could run the following code in C++. If we call Fortran, this will actually give us the Fortran code of the symbolic variable. We can also call LaTeX on it, which will give us the LaTeX code to type up in our documents. MATLAB function will convert the symbolic expression to a function handle. So now we're going to look at a summarizing exercise where we will use this code generation and the symbolic toolbox. And so in PDEs, to test your method, there's a method of manufactured solutions. This is where we're going to solve for right-hand side B, so we know that our solution would have an exact solution. We know that our system would have an exact solution. So B is going to be called our forcing term. We're going to consider the structural equilibrium equations, and we'll see that the calculus part of the symbolic toolbox will be very useful here. So we want to compute B in terms of all of these other variables. If we solve this system for forcing term B, an artificial right-hand side, we know that B is going to be equal to the negative divergence of P divided by rho 0. So to compute B, we first need to start with F and work upwards to compute P. So F is just going to be given by the identity matrix plus the Jacobian of this given vector U. E is given here. It's going to be formed by the adjoint of F. In computing S, we need to take the trace, meaning the sum of the diagonal entries of E, and then compute P as S times F transpose. So if we look at the following example here, I'm supplying you with the following displacement field U, and we want to compute the corresponding vector term B. What I'd like you to do would be to generate the code in MATLAB, C, and Fortran to compute the forcing term above, and we'll see how those look and differ from each other. The starter code is available in manufactured example.m, so let's take a look at that. So here you'll see we've initialized our symbolic variables. We're going to need several. We need x1, x2, and x3 since this is a three-dimensional problem. U is our displacement field. We also have these scalar variables lambda, mu, which are appearing in S, as well as rho, which is appearing in our expression for B. So let's try that exercise and then resume. Welcome back. I hope you enjoyed generating various codes in different languages all throughout these simple functions in MATLAB. Let's go over the solution together here. So you see the first step is we need to compute F. So we first compute the Jacobian of U. This is very simple. We get the Jacobian matrix by specifying Jacobian of U, and we need to say with respect to X. Here we've defined X to be the following vector in R3, as given in the starter code. Then F is just simply going to be the identity, 3x3 identity matrix plus du dx. On such a small example like this, it's fine to form a 3x3 identity. We don't need to use sparse storage. That would only be if we have a matrix that's thousands of dimensions. Then we can simply form E by doing our standard matrix computations on this symbolic matrix. So E is given by 1/2 times F dot transpose times F minus I3. So we're taking the transpose of this matrix. And then S is going to be given by lambda. We can call the trace of E. This is another linear algebra function that is defined for symbolic matrices. We need to multiply this by the identity since trace is a scalar, and then add 2 mu I. And then the expression for B is very simple. It's just equal to -1 divided by rho times the divergence here. Now B is in R3, so we know that the divergence so for B1, it's going to be taking the divergence of the first column of P with respect to X. B2 is going to be given by the divergence of the second column of P with respect to X. So this is the argument where we pass in with what variable are we taking this divergence operation. Then we can generate the MATLAB code by just calling MATLAB function, Fortran code, C code, as well as LaTeX. So now let's look at these following outputs. So I've run this on the Corn system as such. So for MATLAB, you see that it's returned a function handle. And of course, for this, we have 6 independent variables. We have x1, x2, x3, lambda, mu, and rho. And it's given it in the corresponding format of MATLAB syntax. And then for Fortran, you'll see that we give it's specified by B11 since Fortran is 1-based indexing. So we get this very messy expression of the corresponding Fortran code that is generated by this function handle. So B11 is given by this argument. Here's B21 as well as B31. The C code we'll see, instead of having the parentheses, is given by the square brackets, and it's also 0-based to note. So now we have B00, B10, B20, etc. And you could copy and paste this into C, and this code would run, as well as the Fortran code in Fortran. Lastly, you'll see we've been given the LaTeX code here. So this is typing up the symbolic expression for B in MATLAB in LaTeX format to be used within your reports or homework assignments.